In this video, our goal is to be able to understand how to determine the mean or average observable. So I'm going to write it down over here. On our previous video, we determined how to obtain the observable of a linear momentum from this particular equation here, where px, which is our operator, is multiplied by our eigenfunction, and that equals to our eigenvalue, which is a, which is also reproducing our eigenfunction. Now, where our operator in here is actually equal to negative I h bar multiplied by our partial derivative with respect to x. Now, the operator that will be applied to the eigenfunction, which is represented as f, in order to produce an eigenvalue, which is represented as a, that is observed as a during the measurement. So in this particular case, once you are able to actually apply our operator to our eigenfunction, we get our eigenvalue that is observed during a measurement. Now, therefore, for the calculation of our a, which is the observable for our linear momentum operator, which is expressed as a, which is linked from our operator or extracted from our operator, then we can actually determine our a with respect to our eigenfunction, which is f. So where f in this case here is equal to, let's make it as psi. Now psi in this part here equals to e I k x. So what we realize is that we put this f here into this equation, and our p, which is our momentum operator as expressed as this, into this equation, we realize that, hey, our a is actually equal to h bar multiplied by k. Now, where k is actually a constant, and this h bar is actually equal to our Planck constant divided by 2 pi. So once you're able to understand what a is, our next step is to be able to understand what a normalized wave function is. And this is the second part of our explanation in our for we to introduce our idea of average observable. Now, we know what a is. We also understand that a normalized function is expressed as this, where this is actually the integration from negative infinity to positive infinity, and we are doing that with our psi complex conjugate multiplied by our psi here with respect to dx. And what we realize is that by normalizing, it's all equal to 1. So what we see in here is that this is actually expressed in quantum mechanics here, and this describes a state. So what do I mean a state? A state is kind of a little bit of a circle here, where you have different systems. Let's say we have triangle systems with different sizes, and we have another system which are all bubbles in here with different sizes. Now, we can actually express a system which is a triangle system that is actually in a state with respect to the system's mean or average observable. So this mean or average observable of our system here will be actually expressed in terms of a, because a is our observable, and we are using the observable for a particular property, which is in this case a triangle. We can express a to be in this particular format with respect to the average observable, where we use this particular arrow bracket in here. So take note in here that in this particular case, our a is actually with respect to our operator, which is this particular a, capital letter A over here, And also what we realize is that once we're able to correspond our average observable A to that of our operator, which is this particular A over here, then we can actually express our mean observable, which is this, in this particular formula by combining our normalized with function with respect to our operator, which is corresponding to our observable A, small a. So in this case, where our integration is actually performed in all space, then we realize that, hey, my complex conjugate of psi in here is multiplied by our operator, which is big letter A, and our operator is applied to our function, which is psi in here, and this is actually done in all space. Now take note in here that in this particular part, this actually defines our expectation value, and our psi star over here is actually expressed as the complex conjugate. And why do I call this complex conjugate? The reason why I call this complex conjugate is to be able to differentiate this particular one from this particular psi in here. Why is because this psi here takes into account the fact that our I is actually changed to negative I, while our regular psi in here without any star just takes into account all the i's. Like for example, on our previous video or on our previous section here, we have I in here. This is actually an expression for just our regular psi. However, if I'm using psi star, that is actually having a negative I in here. So moving ahead here, what we realize take note is that the combination of both our A, which is our operator, and our psi is really important for we to be able to determine our mean or average observable, which is A. So in this particular part, once you're able to understand that this is actually a representative of one particle in all space, then we can actually explicitly express this formula that is for one particle in a 3D space. So in a 3D space, this is actually rewritten as follows. So we have A to be equal to, which is the mean or average observable, to be equal to 3 integrations, all from negative infinity to positive infinity, and our complex conjugate is actually with respect to x, y, z, and our A on the other side, which is our operator, is applied to our regular psi in here, which has its own x, y, z in there, and all this is actually with respect to dx, dy, and dz over there. So take note that applying the operator to our psi in here is actually done first before actually integrating everything in there. So once you're able to look at this in the 3D state, now our next one is to be able to look at how can we be able to actually apply this into the real world. Now one way you can do that is by using harmonic oscillator. Now for an harmonic oscillator, what we realize is that we are expected to actually determine the average kinetic energy. So if you're asked to determine the average kinetic energy, which I'm going to express as the arrow bracket with a T, then let me just rewrite this. We need two things in here, because remember in our previous section here we said we need our operator and we need our wave function. So in this case, if you're given our wave function, which is expressed as where our R4 equals to bar over there. Now we also need the other part, which is our operator. So if our operator for this t equals to, then it means that you're going to apply the derivative 2 times before you're able to our wave function in here in our for way to then determine the integration and obtain our average kinetic energy. So in this particular case, once we go back to our original formula, which is what we have over here at the top, we rewrite this as t equals to this in all space. This is actually equal to, you put all these variables into this equation, and what we see is that, so once you're able to actually expand all this by analysis, what we realize is that our average kinetic energy is actually equal to infinity when you look at it in all space in here. So that's about it for actually understanding the average observable, which is our example that shows you the average kinetic energy with relationship with the wave function and its operator in there, in order for we to understand more about a system that is actually placed in a particular state. All the same, thanks for following me through this. I truly appreciate it. Please hit the comment down below. Let me hear your thoughts. Thanks for the support. By that way, I can talk to you all later. Be smart.